All right, here we go. Today we're going to be doing a sample problem in which we deal with what you'll kind of call like hinge problems. You're going to see a lot of stuff with a hinge today. So we are going to look at a situation like a castle. All right, so you got a castle here. Okay, and then we have a drawbridge coming out, and that drawbridge. Okay, there we go. Drawbridge, but obviously that's not. So we're going to look at literally the bridge. Now this is not going to be super easy to actually draw anything on, so we're going to shift this to the side real quick and draw the castle like this. If you didn't know this, which I wouldn't blame you for not, most people don't, the way they did hinges on old castles was just a little bit of a ledge right here. Okay, and we're going to have a cable coming down, attaching right here. And we're going to say that that it's not actually hitting the ground on the other side. It is currently entirely held up by this cable. Arguably, it's two cables, but we'll just treat it as one right here. It's kind of the combination of both of them in that particular case. And walking across this bridge will be Night Horse, okay? Which is a horse. There's a knight on it. So let me attempt real quick to draw a knight horse.
Why wouldn't that be a
James, clearly we're not asking questions.
Now, what was the question?
Why wouldn't you say a knight on horseback?
No. Now, the answer to that question is something that has plagued me for years. I made this joke that it was knight and horse and night horse quite a few years back, but I haven't drawn a horse head yet, so hold on. I'll be right back. I'm not great with the head, I'm not going to lie to you, but like...
There was one time I drew a really nice horseback.
Hold on, I got this. I got this. We're important priorities here, people.
Oh, is that a mouth?
Nailed it.
Oh,
Night horse. Yeah. Oh wait, it's got to have a mane. Okay. Night horse's name is Sarah. All right. Anyway, so we talked a few years back about this. Here's the thing. I kind of hate this, and I realize that wouldn't it be so much cooler if instead of teachers going by their legit names, if it was like a band, like you got to like name like your presents or whatever, like instead of saying like who do you have physics with, Mr. Spain, or you'd be like who do you have physics with Night Horse. Night Horse is who I think, and like I come in with like pyrotechnics, I'm like, it's time for physics, let's go, and they're like, and we still do physics, just entirely normally. It'd be boring and difficult and all that sort of fun jazz, but at least kind of the surrounding stuff would get you like more amped, like let's do this thing. Okay, so last hour they were more amped than you currently are. It's fair. It's 6 hours. You're tired. Whatever. They don't fake it. Okay, so what I suggested is, what if we made merch? And some people got really excited about the idea. They're gonna walk to college wearing a Night Horse T-shirt. Like, ooh, did you like see them in concert? Like, no, this is my physics teacher. And then we have like tour dates on the back, but it says like Tuesday, you just like stayed at home and watched the kids or whatever. Like, because it would just be that's what me, just like I'm not touring anywhere. But like Tuesday, Alton, Wednesday, Alton, Thursday. Well, actually, like 3 days in a row he was missing because apparently his kids are sick all the time. Anyway.
Realistic.
For real, right? Anyway, so I think someone's going to actually do the art for Night Horse. We also have an AI attempt right now, but yes.
Okay, so I want to make a collage of your face on a t-shirt.
No, we're not doing that. That feels too weird for me and too me specific. I don't love it.
Well, it doesn't. Well,
we can do Night Horse. I'm cool with Night Horse. I don't love Night Horse face on anything for that matter. Okay, so let's move on to the legit. So that was the idea of Night Horse. Also, I love creating problems and motifs around problems that allow you to like talk to previous years and be like, have you guys got to the Night Horse problem? Like the last 5 years, you could probably say like, have you been to the Night Horse problem? And they'll be like, yeah, we know exactly what you're talking about. Or the hobo kicking thumbs off the side of buildings problem, or things like you don't remember this from kinematics when we kick the thumbs off the side?
The hobo kicking the thumbs.
He was barely paying attention.
Exactly. I was barely.
Anyway.
Did I miss that though?
Apparently, I don't know. Yes. Okay. Moving on. Or the I'm sure that you might have been asked already about the Peter Griffin problem, like knowing like you could sell them that, and then so I love creating these ridiculous situations just so that from year to year to year you can like talk about the. Anyway, moving on. So here's Night Horse. 9 horses is not a new problem. We've done it before. Let's put some numbers to this so that we can actually before we do numbers, let's do an extended force diagram. You will note the extended force diagram is remarkably similar to the one you did just a minute ago. Also, if the drawing itself, again, is getting in your way, what you want to do is the following. Instead of a bridge, you can, again, just draw a line to represent that kind of lever arm and go from there. I will show both options. You choose whichever one you find to be easiest. All right, what forces go on this? Gravity, cool. So that would be in the center right there. So we would draw a force of gravity in the center right there. Next, tension. Okay, which way does tension go? Up and to the left. So of course that would go here, and that would go here. Next. Let's wait on normal for a second. You're not wrong in the slightest. I want to talk about it. Okay. Next.
Horse. Or first on horse? Is that a horse?
Who is that?
Horse. Oh, a
Night
horse.
Night horse.
That's night horse.
What is that?
We've talked about
I got it right.
What is that symbol?
You know, you do your best. You try to train them. You try to teach them how the way the world works. Go out and they call it, is that a person on the... All right. Wait. Moving on. Moving on in the ridiculousness. All right. So, to that particular point of normal going to the right, yes, probably normal is best. And probably normal up is also best. You can kind of see it from the picture. But the reason we want to talk about a hinge is the following. Okay, coming over here, I will regularly talk about this with a hinge, because if you imagine a door, on the side of a door is what we call, obviously, a hinge. You know this. It's the brackets that are over there. And the nice thing about a hinge is that a hinge can provide a force, since it's in a circle and there's a post in the center, it can provide a force in every single direction that we possibly need. If the door gets pulled that way, the hinge pulls the opposite way. If we need a force up and to the right, the hinge can do it, or down and to the left. Okay? The way you do that is, like I said, you do a circle, okay, and it can point whichever the heck way you want in that particular case. Now, you can see from the picture pretty well which way these are supposed to go, but that's not always the case on every single problem. So instead of normal, what I would suggest we say is, let's just call this force a hinge. Now, which way is force hinge going to point? Sort of. The correct ultimate way of force hinge, you're not wrong, but the correct way is up and to the right.
Yeah.
Okay? But we can split this up into its components. And we can just leave it as its components and say, hey, we'll call this force hinge horizontal, okay, or force hinge in the X, and we'll call this force hinge in the Y. And of course, force hinge is, as itself, a total, is just the vector addition of both of the two of these together, if the problem asks for that at the very end. Whether it asks for that at the very end, this is how we're going to start, because we can deal with that either way. All right, we need some numbers here. What is a decent mass of the bridge? It's a giant oak. What did you say? 200 kilograms? Or that'd be 400, 500 pounds? All right, fair enough. All right, 200. Bridge, 200 kilograms.
We'll say this is
Cool. All right, so we have a horse walking across the bridge. It is a horse, of course. Of course. How heavy would a horse be? 800. Well, what's so heavy? Like 800. That's a lot. That's a heavy horse. But like, just in pounds, what do you got?
Probably like 150 pounds. So.
No. It's definitely like
It's
300.
a full-grown male right there.
300.
What's that? 300, 400. Let's go 300. Okay. Now there's a knight on there. Okay. How heavy is the knight in pounds?
you gotta add
100 pounds. Pounds?
Oh.
Like a fourth grader knight? What are you talking about? 200. All right, but we got to put armor on him, so
250.
250. What do you think how armor is? You know how heavy armor is?
Yeah,
It says 930 pounds for a
That
horse.
sounds about right. Okay, I like 930 pounds. So we'll go with 9 for a horse. What do you mean for a horse like that's big? 900 pounds is a horse. Have you seen a horse? All right, 900 pounds is normal. You can obviously get all sorts of different sizes. Let's do 900. Cool. 900 pounds. The humans, how big?
250.
250. Cool, because armor is typically somewhere on the range of 50 to 80 pounds that they carry around.
Yeah, right.
Let's go ahead. 900. We'll throw a 300 pound between the armor and everything. We'll go 1,200 pounds on the knight. So, 1,200 pounds.
Is he gonna break?
Yeah, is he gonna break the bridge?
Probably not, no. Our wood is very sturdy. All right, what force is that, though, that we have right there? What is 1,200 pounds? That would be the not massive night horse.
Force of gravity.
So we can just say, for our purposes, that is the force of night horse. See conversation yesterday about the fact that technically that's gravity, but not gravity. Okay.
I love that. I'll never forget about it. I hate how that's
Never forget about night horse.
Never
Sweet.
I'm gonna forget when I go home.
Me too.
Hopefully not. It's part of the work that you're supposed to be doing. All right.
No.
Both of you have faith.
I'm fully sold.
All right, our goal is similar to the goal from yesterday when we were trying to find the force of the first pillar and the second pillar. Our goal right now is to find what is tension. I do realize I need to give you one other number. Okay, and then we're going to try to find force hinge X and force hinge Y. Now, some problems on your homework might ask you just for straight up force hinge. If it does that, you would still want to do the same thing. What would the only thing that you would need to do at the very end with this information to get force of hinge if you have the information provided? Well, not just, thank you, Pythagorean theorem, not just straight up add because they are vectors and not going the same way. All right, now the other thing that you're going to need is this. Let's just go ahead and use geometry and ask, what angle is that right there? It's probably close to 45. I think I angled it just a little bit up, and that's on purpose because I want you to see which is the correct angle to use. Obviously, if it's 45, it's kind of harder to spot. So let's just make it a little bit less than 45. Let's say 40. Okay? All right. With the information provided, you should now be able to get everything that is right here.
Right.
So this is a bridge problem, so it's an equilibrium problem, which means you know that sum of forces are equal to 0 and sum of torques are equal to 0. Similar to yesterday, you can probably already see that sum of forces is a bad idea because I got a bunch of stuff that I don't know. So I probably want to start with sum of torques. In order to start with sum of torques, what is the first thing you have, assuming you've done all this, obviously, you've done the extended force diagram, you've done this. Before you do any of the math, what do you have to do first?
Set the fulcrum.
The fulcrum, correct. Torques don't mean anything until you set the fulcrum, and who sets the fulcrum? Now, I want to highlight that very particularly because all of you could do this same problem and put the fulcrum in a different location and it be correct. There are by far easy spots to put it, and I'm happy to do that. But please understand, this is why it's very important when you do your work to tell me where your fulcrum is. I'm not just going to assume. Where is the most logical place to put the fulcrum in this particular scenario? At the hinge. Why? Sort of. I hear what you're saying. There are two forces over there. That being said, even if the fulcrum wasn't there, do both of those forces cause torque actually? No. Which one does not cause torque regardless of where the fulcrum's at? Force of hinge in the X is parallel to the lever arm. So, but still, I'm with you. Let's put the hinge over here. Make sure you show it. Now the next step is find a color that works. Okay. Sum the torques equal to 0, and you do what we regularly do for forces. Is it going to cause torque, and in what direction? Going left to right. Will either of the two of these cause torque? No. Okay, so I'm going to skip these two. Let's go to gravity and ask, is it going to cause torque? In what direction? That is going to be, I've heard both. It is negative because it should be clockwise in that case. So we have the negative torque. Is that color okay, or is that hard to see?
That's great.
Cool beans. Okay, next, force of night horse. Will it cause torque? Positive or negative? Negative as well. And then finally, tension. Does tension cause torque? What's it got to be? Positive, we talked about this yesterday. Don't forget that in order to get to 0, you have to have a positive and a negative. If you get to the end of one of these and you have not if you've gotten all negative or all positive, you know you've done something wrong or probably done your extended force diagram wrong, because there's no way that would work otherwise. Now the next step, the next actual step, is plug in your individual equation. That being said, I showed you a trick yesterday. You're welcome to use this, and it's easier to move these around subtraction and addition wise when they're smaller as opposed to written fully out in their form. So since I know that my answer is inside tension over here, I'm going to go ahead and add those two on the other side. Torque of tension is equal to torque of gravity plus torque of night horse. I totally forgot another set of numbers that we need.
Yeah, I'm sure.
My apologies. All right. How long is the bridge?
20 feet.
Interesting thing. Here's an interesting conversation. I'm fine with 20 feet. We'll go 5 meters ish or 6 meters. Okay. So there's what you imagine in your head because of watching fantasy, and there's what is actually probably the case. That is probably closer to the fantasy one, which we'll stick with. It's no big deal. It doesn't mess with anything all that much anyway. Okay. 20 feet is like 6 meters ish, probably a little bit less. We'll go 6 meters. But in actuality, if you didn't know this, actual moats, number one, were not filled with anything. They were pretty much just a ditch, making it hard to get to the base of the wall, and were probably nothing more than like 3 or 4 feet across. So drawbridges were not what we actually have usually picked in our head, but that makes this a kind of a dumb problem when I made a night horse. So what am I being a big deal about? Okay, next we need to know, where is the night horse on the bridge? What distance you want to tell me? What's that?
4 meters.
From where? I got nothing.
5 meters from the left.
From the left, okay. Or that would of course mean something like problem would be like it's 1 meter from the edge in that particular case. Yes, I know I'm being a jerk, but I think you can figure this out no problem, and there's reasons why I do it. Okay. Coming back. Apologies for not giving you distances earlier. All right. Back to our regularly scheduled programming. What's the next step? Algebra here. Expand, fill out those individual equations. What's my equation for a torque? Lever arm of tension times. Should I have sine? We kept using 1 the other day.
Yes.
Why do I need to use sine right here? If there's an angle, it's not perpendicular. Correct. Moving over to torque of gravity, I have lever arm of gravity times force of gravity. Can I multiply by sine on this one? Or what is the angle for gravity? Yeah, you can see it right here. What is that angle? 90. So yep, I can sine of 90 is 1. So I'm just going to multiply by 1 there. Or if you want to write sine of 90, you're certainly welcome to do that. Okay, plus night horse. So we need the lever arm of night horse times the force of night horse at the end. Algebraically, this one isn't bad. I'm looking for that, so I'm just going to divide by these two at the same time. I'm totally going to cheat.
Don't like it for that.
Sorry.
How dare you cheat?
Just gonna.
That's not collegiate.
It's not. It sort of is. See conversation about when it's appropriate to use AI. AI is not a bad thing, but if you're using it correctly, it's just fine. As a matter of fact, based on conversations I've had with current college students, most college professors will say the literal exact same thing. All right, moving on. Do you know what the difference is between doing good AI and bad AI? Like using it well? Not entirely that. I mean, let's just be like writing a paper real fast. Sorry, quick aside, people online. Okay, writing a paper. What's good use of AI versus bad use of AI?
Check outlines. Check lines.
Even better than that. You can have it write a paper. I would say straight up, let it write your paper. What's the difference between good AI and bad AI?
Copying the paper and using it as inspiration.
Read what it says and change it so it's better. Change it so it's you. Change it so that like you read the words and you go like, that sounds like a dumb way to phrase that. I'm going to rewrite that particular sentence so that it's more constructed in the way that I. Basically, AI is an amazing way to get over the bubble of I know nothing to I want something on the page, and take the thing on the page and start thinking. Just be like, That's kind of a dumb way to phrase that guy. Maybe that should go over here. Maybe this should go over here. I probably wouldn't have said that way. Take this sentence out and write it the way that you would actually write it. Literally, read it. Basically, here's what AI does amazing that is awesome. If you're using AI as a rough draft, you're cheating. If you're giving AI a rough draft and then taking it and making a second, third, or fourth draft, that's fantastic. Do that. Moving on. All right. Plug our numbers in. What is the lever arm for gravity?
3 meters.
Should be 3 meters. Yep. Right here, halfway. We didn't calculate these yet. Man, I did this in a backwards order compared to last hour. Last hour I was on it. All right. How do I need to calculate force of gravity? Yeah. So I got mass of bridge right here, so I'm just going to take this over here, and the force of gravity is just going to be mass of bridge times g, or 200 kilograms times g, or what is that, 1,960? Sweet. Okay, and then of course I got 1,200 pounds on night horse. What do I need to do for that?
Get to Newton.
Convert, so yep, 1 pound is equal to 4.45 newtons. So what is night horse? Something like 4,000, what's that?
5,300.
5,301?
40.
40 is fine. Cool. So now coming back over here, we know 3 meters is FG, so FG was that, wasn't it 1920? 60, thank you. 600 newtons. Plus, what is the lever arm for night horse? 5 meters, because you're going fulcrum to where it's applied. So, yep, it'd be 5 meters. What is the force of night horse? Just calculate. 5340. Cool. What is the lever arm for tension? 6 meters. And what is the angle for tension? Nope. What is the angle for tension? I did this on purpose. This is why I didn't allow it to be 45.
You are so mean.
I am, but also it happens a lot, and so that's why I'm trying to just call your attention to it. What does the angle need to be? 50. Now let me show you why, and let me show you where it pops up on your homework so that it's less of an issue when it pops up on your homework, because I know it's going to. Someone came into my advisory today and we talked about it. Isn't that right? All right. Okay. So if you look real quickly, force tension, and we split it into its components, here are its components. Here's force tension in the y, and here's force tension in the x. Yes? Which one of those two do you technically need? The y. Or not technically, yes, the y, because it is perpendicular. Yes? So, technically speaking, you could use cosine of 40, but my personal experience is when I let people go back and forth between sine and cosine that they struggle to figure out when to use what. So, if you'll remember, the definition of the angle you're supposed to use is the angle from the lever arm to where the force is applied. Knowing full well that this to there is going to be 90, if that's 40, you need to use 50. Here's an example on your homework real quick. I know this is a quick aside, but I know it's going to matter later. On your homework, there's a problem with a tank. And it says that the wheels of the tank, sorry, this is not very tankish, okay? The wheels of the tank are propped up by 8 degrees. Yes? Okay, and asks how much torque is caused by gravity. Now I'm going to, instead of drawing this, I'm going to kind of expand it out to a line. Here's 8 degrees, and here's force of gravity. What you want is how much force of gravity is perpendicular to the lever arm. But as you can kind of see from the picture, that's not always easy to spot and not always easy to see. So what you want to do is you want to say, all right, I know that the angle I need to use, I can easily do this, is from the lever arm to the force. Then look for the triangle. If that's 8 degrees, then guess what this angle is here?
82.
It's a complementary, right? Because this is 8, that's 90, so the other has to be 82. Yes? So coming back here, Okay, I am not going to. I'll tell you right now, I would not get mad on a problem like this if you chose to use cosine instead. Okay, if you chose to use cosine of 40, then obviously you figured this out. But I'm telling you, that's harder to remember. It is way easier to remember. Let's just always use sine. But your angle, as I mentioned before, must be from the lever arm to the force. Then when you make this triangle, notice that here's 50. The opposite of 50 is force tension in the y, the one I'm looking for in that particular case. Make sense? Cool beans. All right. Plug it in. What do you get?
7,836. 7,000. 0.
Got you. 7,000. 0.3. What?
7088.32.
What are you giving me decimals for? 7,090. Thank you.
Oh. Not even 90.
Yes, 90. Goodness, that's 3 significant figures. Let me ask you a question. If this was a decimal, would you have any issue whatsoever rounding to 0.009?
No.
Yeah,
I
would.
I would.
Then
I always do 4.
You need 4. It's 3 significant figs is what you need.
Okay,
All right.
well,
3 sig figs. Moving on.
More gets you is keto.
If you don't like it, suck it up. Moving on. Here we go. Okay, now, here are your options. That is force tension. That's force tension right there. Now, the original question asked. Make this a little bit smaller so it's easier to see. Cool. Knock this out. Force hinge in the x and force hinge in the y. What's up?
I crossed it off my list too.
Cool. Okay, force tension. Force hinge in the x and the force hinge in the y. As we mentioned yesterday, your first option to find other things is move the fulcrum. Okay? If you decided to move the fulcrum, make sure that on your page that you put another x and you actually label them like subscript like 1 and 2. If you moved your fulcrum elsewhere, we could find this guy right here. But what would probably be our easier bet? Sum the forces. Now, unlike yesterday, though, we do not just have in the y, which was yesterday's, so we do have to sum the forces in the x and sum the forces in the y. It's not all that bad. That was pretty intense. All right, so here we go. Sum the forces in the y equals 0. Looking at your picture, you just do what you always do for this. Is it in the y? What direction? Is it only in the y? Okay? Who was that? Was that me? Was that me saying that? All right. Running the... Fair enough. Go back to sleep. All right. So starting over there, what forces should be in the y? Positive force hinge in the y. Keep going. Minus force of gravity.
Minus force at night force plus force tension in the y.
Correct. And I'm happy that you said in the y because, yes, that is not in that 7,090 that we have earlier is in both directions, so we have to calculate it in the y. In essence, once again, here's what this equation actually says. Hey, everything pulling up better equal everything pulling down, right? Makes sense. Now, algebraically, it's not that hard. We're looking for this guy, so I add these two on the other side. Force of gravity plus force of night horse. Why? Because those are the two going down. Everything up has to equal everything down. But if I subtract off how much tension is pulling up, the remainder better be what the hinge is pulling up with. Force of gravity is just straight up known, 1,960 newtons, yes?
Yes.
Force of night horse is also straight up known, 5,340. Okay, how do we get tension in the y? Trig, so?
790. Is it cosine?
It depends on which angle you choose. I don't care, but I would choose the easier one. What's that? I would probably do sine 50, especially since you've already transferred it that way. I think that would be easier. But, of course, cosine of 40 is, in fact, the exact same amount. So you're fine. What's up, James?
When I plugged it in, I got a different number. That plug opened
To get the 7,000. Okay, let me just check. Make sure that you're not in radians. Okay, I'll just check real quick. 960 plus 340. Well, that'll do it right there. Actually, I was doing the wrong one anyway. 3 times 1960 plus 5 times 5, 340, divided by 6, and divide by sine 50. Yeah, it's 7,090. Like on the dot, there are no extra numbers. No, sorry. And then 1960 plus 5, 340. Yes. Yeah. Sine of 50. All right, so I got 1,870. 1,870 newtons, and no, that was actually 1,868, and I rounded to 1,870. All right, now on this, by the way, since this is a component, I would highly suggest whenever it's a component, which this is, you get used to always doing that. Okay, that's a y hat on that because that is just in the y, not in the x, or not a total. All right. Coming back over here, checking our list twice. Oh, sorry, oops, backwards. The wrong one. We did the y, so what do we need to do now?
X.
Arguably, the x is by far the easiest one. Why is the x the easiest one? There's only 2 of them. So what are the sum of forces in the x?
Force hinge in the X.
Positive and negative on that?
Positive.
Yeah.
Minus force tension.
Minus force tension in the x, which again makes really good sense because after I do my algebra, here's what it says. It says, hey, as much as the tension is pulling to the left, the hinge has to press to the right. Of course it does. Okay, how do I get tension in the x? So that should be 7,090 newtons cosine of 50. $4,560. And like I said, that is x hat on that guy right there.
I think I can.
What is that?
4,560 newtons x hat. Now, like I said before, that is the components. So just a reminder, if the problem had instead said, what is force hinge? What's the only thing you would do now different? Pineapple theorem, yep. Pineapple theorem to, of course, get the hypotenuse. Or the other question that certainly could be asked is, what angle is it applied at? Which is just as easy. What would we do then?
Inverse tangerine.
Inverse tangerine, yes. Inverse tangerine. Yes, sir. That would be inverse tangerine. All right. And that's the problem that I have for you today. Any questions, concerns on how we did what up here?
Oh, I actually like feel okay.
Cool beans. Cool beans. All right. Done with that one.